Welcome to chemistry classes. In this video we are going to discuss about subshells and atomic orbital. Subshell and atomic orbital. A-level chemistry chapter 2 part 2. Subshell and atomic orbital. We already discussed nucleus. Around nucleus there are energy level. Okay, first energy level, second energy level, third energy level. These energy levels are called orbit or shell, or we can say principal quantum shell. Okay, this principal quantum shell or main energy level, this energy level again consists of subshell. Okay, so look here, this is nucleus. Around nucleus this is energy level, first energy level, second energy level, third energy level. These energy levels are called principal quantum shells. Principal quantum shells are represented by n equal to 1, n equal to 2, n equal to 3. This is first principal quantum shell, second principal quantum shell, third principal quantum shell, etc. Okay, so this principal quantum shell again consists of subshell. Subshell mean these subshells are represented by S, P, D, F, etc. Main energy level, again there are some subpart. Okay, there is electron. This subpart or subshells are S, P, D, F. Okay, it represented by S, P, D, F. And here, look here, we know these are the principal quantum shell, n equal to 1, n equal to 2, n equal to 3. In first quantum shell, we want to find number of subshell in first energy level. So we can do n minus 1. n minus 1. Here n equal to 1. 1 minus 1, 0. Okay, n equal to 0 mean here number of subshell 0 mean here these are the values. Okay, 0 mean here only one subshell, it is S. Here n equal to 2. n equal to 2 means second energy level. You want to find number of subshell in second energy level, so you have to do n minus 2. We know n minus 2, here n equal to 2, sorry, here n minus 1. Okay, n minus 1, here n minus 1, n minus 1, here n equal to 2, 2 minus 1, 2 minus 1, it is 1. 2 minus 1, here 1, 1 mean P. So here there will be two subshell S and P. We got 1, so there will be two subshell S and P, two subshell. In second energy level, there will be two subshell S and P. You want to find third energy level, number of subshell in third energy level. So n minus 1, n equal to 3. 3 minus 1, it is 2. 2 mean it is D. So here 3 subshells S, P, D. There will be S, P, D. These are the number of subshell in first energy level, second energy level, third energy level. So remember, in first energy level there is only one subshell, S subshell. In second energy level there are two subshell, S and P. Third energy level there are three subshell, S, P, D. Clear? So here we discuss principal quantum shell. Principal quantum shells n equal to 1, 2, 3. Okay, this principal quantum shell again consists of subshell. Subshells are represented by S, P, D, F. S, P, D, F. Okay, here we want to find number of subshell in each principal quantum shell. So we can use this equation n minus 1. Here first energy level n minus 1, 0. Okay, 0 mean only one subshell, S subshell. Okay, n equal, here number of subshell 1 mean, number of subshell you got 1 mean there are two subshell S and P. Here after solving this you got 2. 2 mean there are 3 subshell S, P, D. Clear? So there are different type of subshell S, P, D, F. These are different type of subshell. Okay. In S subshell we can accommodate maximum 2 electron. S subshell maximum 2 electron. P subshell we can accommodate maximum 6 electron. Remember this, S subshell maximum 2 electron, P subshell maximum 6 electron, D subshell maximum 10 electron, F subshell we can accommodate maximum 14 electron. Okay, so principal quantum shell consists of subshell. Okay, there are different type of subshell S, P, D, F. S subshell maximum 2 electron we can accommodate. Okay, P subshell maximum 6 electron, D subshell 10 electron, F subshell we can accommodate maximum 14 electron. Clear? Okay, next one we have to discuss here arrangement of subshell according to their energy. Arrangement of subshell according to their energy. Okay, so we discussed there are different type of subshell. Each principal quantum shells consist of different number of subshells. So we can arrange subshell or electrons are filled in subshell according to their energy. Subshell with lower energy fill first. Okay, so here subshells are arranged according to their energy. Okay, so see here you can see this figure. This graph represents subshells and the arrangement of subshell according to their energy. So we can write it like this: 1s, 2s, 2p, 3s, 3p, 3p. After 3p there will be slight difference there. Okay, so look here, generally we can say 1s, 2s, 2p, 3s, 3p, 4s, 3d. Till argon it is okay. But after argon, some situation here 3d first, then 4s. Okay, so there is some slight variation in their energy, subshells energy 3d and 4s in different atoms. Okay, after argon, some situation, some elements, their subshell energy variation. Okay, there will be some variation in their subshells, energy, arrangement of energy. So generally we can say 1s, 2s, 2p, 3s, 3p, 3p. After 3p, 4s, 3d. After argon, 1s, 2s, 2p, 3s, 3p, 3d, 4s. Okay, so you remember this order. Later we had to write subshell electronic configuration of different elements. So better you just remember this according to their order. Also you remember after argon there will be 3d, 4s. Okay. Okay, next one we have to discuss here atomic orbital. We already discussed here principal quantum shell. Principal quantum shells consist of subshell. Each subshell consists of atomic orbital. Orbital means a space around nucleus. There is more possibility or probability to find electron. Okay, space around nucleus, there is more probability to find electron. Such space called orbital or atomic orbital. So we discuss principal quantum number. Principal quantum number consists of subshell. Subshell consists of different number of atomic orbital. We know there are different type of subshell S, P, D, F. S subshell consists of 1 atomic orbital. P subshell consists of 3 atomic orbital. D subshell consists of 5 atomic orbital. F subshell consists of 7 atomic orbital. Okay, S orbital 1, P orbital 3, D orbital 5, F orbital 7 atomic orbitals. Clear? So remember this. Okay, After that, we have to discuss here shapes of orbital. There are different type of orbital. Okay, so here we have to discuss here. Shape of orbital. First one, S orbital. Okay, here we have to discuss here shape of S orbital, shape of P orbital. Okay, so here we discussed different subshells. They have different number of atomic orbital. Okay, S orbital, there are one S orbital, there are three P orbital, 5 D orbital. Now we have to understand shape of S orbital and P orbital. D orbital, you will study shape of D orbital later. Now we have to discuss shape of S orbital and P orbital. Okay, here basically you have to understand orbital means space around nucleus. There is more probability to find electron. All orbitals, they have three-dimensional shape, 3D shape. Okay, first one we have to understand S orbital. S orbital, they have spherical shape. S orbital, they have spherical shape. Okay, look here, 1s orbital, 2s orbital, 3s orbital. 1s orbital mean your principal quantum shell, first energy level. Okay, S orbital in first energy level, S orbital in second energy level, S orbital in third energy level. We know around nucleus, first energy level, second energy level, third energy level. Okay, so here S orbital in first energy level, it is 1s. S orbital in second energy level, that is 2s. S orbital in third energy level, that is 3s. Okay, all S orbital, 1s, 2s, 3s, all S orbitals, they have same shape, they have spherical shape. Okay, but they have different energy. We know energy level that is close to nucleus, they have less energy. So 1s orbitals less energy than 2s, less than 3s. Okay, main energy level going away from nucleus, their energy will be increases. So this is the order of energy. 3s orbitals has higher energy than 2s, higher than 1s, but they have same shape. All of them are spherical shape. Clear? So here we discussed each subshells consist of different number of atomic orbital. These are the number of atomic orbital. S orbital 1, P orbital, S subshell which consists of 1 atomic orbital, P subshell 3, D subshell 5 atomic orbital, F subshell consists of 7 atomic orbital. Okay, all atomic orbitals, they have three-dimensional shape. Okay, atomic orbital means space around nucleus, there is more probability to find electron. S orbital spherical shape. There are different number of S orbital, 1s, 2s, 3s, 4s, etc. All of them are spherical shape but different energy. Clear? Okay, next one we have to discuss here P orbital. P orbital has dumbbell shape. P orbital dumbbell shape. You can see here shape of P orbital. This is the shape of P orbital. This shape called dumbbell shape. Dumbbell shape. Okay. Here we know S orbital, there is S subshell, there is only one orbital. P orbital, P subshell, there are 3 orbital. Okay, 3 P orbital. These are subshell S, P, D. S subshell 1 orbital. P subshell, there are 3 atomic orbital. So we are talking now P orbital, orbitals of P subshell, that is P orbital. There are 3 P orbital. These three p orbitals are represented like this: px, py, pz. These are the three different p orbitals: px, py, pz. These three p orbitals, they have same energy. Okay, px, py, pz, they have same energy. Also they have same shape. They have same energy and they have same shape. Clear? Look here, we know these are main energy shell, principal energy shell. First principal quantum shell n equal to 1. So there is only one subshell S. Okay, n equal to 2. Second energy level, there are two subshell, S subshell and P subshell. So we will say n equal to 2. So we will say this is 2s and this is 2p. This is 1s. Okay. 2s and 2p mean S orbital of second quantum shell. Okay, p orbital of second quantum shell. So 2p, we are talking now 2p. 2p mean p subshell of second quantum shell. Okay, so we know p subshell, it consists of three orbital. Which are three orbital? px, py, pz. This is I am talking here. Okay, this is 2p. P subshell of second quantum shell. It consists of three atomic orbital. These are px, py, pz. So we can say 2px, 2py, 2pz. Okay. Three different atomic orbitals of 2p we can call 2px, 2py, 2pz. All of them have same energy and same shape. Okay, this is px, py, pz. Px mean this is we will call lobes of atomic orbital along x-axis, that is px. Lobes of atomic orbital along y-axis, that is py. Lobes of atomic orbital along z-axis, that is pz. So these are different atomic orbitals. They have same energy. Okay, they have same shape. Look here I am given 2p, 3p, 4p. 2p mean p subshell of second quantum shell. Okay, p subshell of third quantum shell. P subshell of fourth quantum shell. Okay, so here principal quantum shell different. This is second principal quantum shell, third quantum shell, fourth quantum shell. So they have different energy. Second principal quantum shell mean it is close to nucleus. Okay, so they have less energy. Fourth principal quantum shell mean it is far from nucleus and higher energy. So here 2p, 3p, 4p, they have different energy. 2p less than 3p less than 4p. Okay, but they have same shape. All of them are dumbbell shape. But look here, 2px, 2py, 2pz mean these are three different atomic orbitals of 2p. They have same energy. But 2p, 3p, 4p, here principal quantum shells are different and they have different energy. Clear? So here we discussed p orbital. P orbital, they have dumbbell shape. Okay, and there are three p orbitals, px, py, pz. They have same energy and shape. Okay, here 2p, 3p, 4p, they have different energy, but 2px, 2py, 2pz, same energy. Here same energy, here different energy, but all are same shape. Clear? Okay, next one we have to discuss here filling of electrons in different atomic orbitals. Electron filling in different atomic orbitals. Okay, so here electrons are filled in different atomic orbitals according to their energy. Electrons are filled in different atomic orbitals according to their energy. Okay, so electrons are filled first in orbitals with lower energy. Lower energy orbitals are filled first. Clear? So here we are talking about electron filling. Electrons are filled in different subshell according to their energy. Lower energy subshells are filled first. We discussed before arrangement of subshells according to their energy. 1s, 2s, 2p, 3s, 3p, 3d, 4s. After argon, there is some slight difference we discussed, but generally we can say 1s, 2s, 2p, 3s, 3p. These are the arrangement of subshells. So we can show this like this. Look here. 1s, 2s, 2p, 3s, 3p, 3d, 4s. Generally we can say like this. This is the filling of electrons. Electrons filled first in 1s orbital, 1s orbital, then 2s, then 2p, 3s, 3p, 3d, 4s. This is the order of filling of electrons in different atomic orbital. Clear? So here, look here, 1s orbital means this is first. Here n is equal to 1, here n is equal to 2, n equal to 3, n equal to 4. Okay, this is first quantum shell, only one subshell. Okay, second quantum shell, two subshell. Okay, and third quantum shell. Okay, third quantum shells, there are different atomic orbital, 3s, 3p, 3d. Here these are the atomic orbitals of second quantum shell, 2s, 2p. Here atomic orbitals or subshells of principal quantum shell 1, it is s. Clear? So here electrons are filled first 1s, then 2s, then 2p, 3s, 3p, 3d, then 4s. This is the order of filling of electrons. Okay, when you are moving from bottom to top, energy will be increases. So lower energy 1s, higher energy 4s. Clear? So here this is one example for electronic configuration. Hydrogen. We know hydrogen, there is only one electron, 1s1. Hydrogen only one electron. So electron, first electron filled. Okay, this only one electron, this electron filled in s orbital, and this subshell electronic configuration of hydrogen we will show like this 1s1. 1s1 means this 1 indicate principal quantum number. Okay, 1s1 mean here hydrogen nucleus, after nucleus principal quantum number, it is 1, n equal to 1. Then there is one subshell. Okay, that subshell contain one electron. This is the subshell electronic configuration 1s1. Principal quantum shell n equal to 1. It contain one subshell. That subshell is s. This s orbital contain one electron. Okay. Similarly, we can do subshell electronic configuration of helium. Helium, there is two electron, 1s2, 1s2. Okay, look here, these are the subshell electronic configuration of carbon, nitrogen, oxygen. Write down subshell electronic configuration of carbon, nitrogen, oxygen. To write subshell electronic configuration, we need atomic number. Atomic number of each elements, carbon 6, nitrogen 7, oxygen 8. This atomic number you can use periodic table and you will get atomic number. Okay, so here to write down subshell electronic configuration, I told you before, better you remember 1s, 2s, 2p, 3s, 3p. Remember this order. Okay, so you want to write subshell electronic configuration of carbon, you just write down 1s, 2s, 2p. Carbon atomic number 6, 6 electrons are there. So 6 electron. So 1s2, 2s2, 2p2. We can write down s orbital maximum 2 electron. Okay, so 1s2, Also this is S orbital, maximum 2 electron, 2s2. This is 2p, 2p, 2p. P orbital we can do maximum 6 electron. I told you before s p d. S orbital maximum 2, p orbital 6, d orbital 10. These are the maximum possible electrons in each orbital or each subshell. Okay. So here 1s2, 2s2, 2p2, 2p maximum 6, but we need p orbital, you can put maximum 6 electron, p6, but we need here only 6 electron because carbon atomic number 6. So here 2, 4, 6. That's why here 1s2, 2s2, 2p2. Clear? Next one, nitrogen 7, 1s2, 2s2, 1s2, 2s2. Now 4 electron. We need 3 more. So 1s2, 2s2, 2p3. Okay, 1s2, 2s2, 2p3. P maximum 6, but we need 3 only because atomic number 7. 2 plus 2, 2 plus 2, 4, 4 plus 3, 7. Now it is 7 electron. Next one, oxygen, 1s2, 2s2, 2p4. Okay, oxygen, 1s2, 2s2, 2p4. Now it is 2, 4, 4 plus 4, 8. So you can do electronic configuration like this. See here one more example here, argon. Argon atomic number 18. 18. Okay, so remember 1s, 2s, 2p, 3s, 3p. Okay, we know this order, 1s, 2s, 2p, 3s, 3p. Then you just put number of electrons here. Okay, s orbital maximum 2 electron, p orbital maximum 6 electron. Okay, also here s orbital, so 2. Now we just count electron, 2, 4, 4 plus 6, 10, 10 plus 2, 12. 12 electron. Now here maximum 18 electron we needed. So put here 6. Okay, p orbital 6 electron. So 2, 4, 10, 12, 18. 18 electron. This is the electronic configuration of argon. Look here, potassium, electronic configuration of potassium. Potassium 19. 19. So here 1s2, 2s2, 2p6, 3s2, 3p6. Now it is 18. Same like this, 18. 2, 4, 10, 12, 18. We need 19. So put one more. So this is electronic configuration of potassium. Electronic configuration of potassium. Look here, this part it is 18. 1s2, 2s2, 2p6, 3s2, 3p6. It is 18. 18 means it is argon. Argon. So in shorthand we can write electronic configuration of potassium like this. Argon in a square bracket, then 4s1. Its meaning here this argon in square bracket mean it represent 1s2, 2s2, 2p6, 3s2, 3p6. After that outer shell electronic configuration 4s1. We will use only noble gas like this. In shorthand you can write shorthand only noble gas. You cannot use other elements, only noble gas. Here argon in a square bracket, its meaning 1s2, 2s2, 2p6, 3s2, 3p6. Okay, 18. It came 18. After that 4s1. Okay, so this is electronic configuration of potassium. So here we discuss filling of electrons in different atomic orbitals. Electrons are filled in different atomic orbitals according to their energy. Lower energy orbital filled first. 1s1, hydrogen electronic configuration 1s1. Here 1 represents principal quantum shell. S represents subshell. Here this 1 represents number of electron. Okay, look here, 2p2. 2p2 mean this 2. Look here, carbon outer shell configuration mean last configuration, that is outer shell configuration. 2p2. 2p2 mean here principal quantum shell 2, that is 2. And here subshell, p subshell, number of electron 2, that is 2p2. 3p here 3p6 mean here principal quantum number 3, subshell p orbital or subshell p, number of electron 6. Okay, you can find principal quantum number, subshell, number of electrons like this. Okay, and here we discuss different electronic configuration. To write down electronic configuration, you have to remember 1s, 2s, 2p, 3s, 3p. Okay, 3d, 4s. There will be slight difference in 3d, 4s, but rest all same. And here we discuss noble gas configuration. We can do like this: argon in a square bracket. Potassium electronic configuration 9d, argon in a square bracket, comma 4s1. This represent electronic configuration till 18. We will use only noble gas like this: helium, neon, argon, krypton. Okay, next one we have to discuss here filling electrons in 3d orbital. Filling electrons in 3d orbital. See here electronic configuration of calcium. This is electronic configuration of calcium: 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Okay, so here calcium, we know calcium there are 20 electrons: 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. These are 20 electrons. Okay, and here these orbitals are filled completely. So after calcium, next element scandium. Next element scandium, there is one more electron in scandium. So there will be one additional orbital after calcium. Okay, so after calcium a new subshell will be occupied. This new subshell is 3d. After calcium a new orbital or a new subshell will be occupied. It is 3d orbital. 3d orbital. Okay, and here here calcium it will end 4s. The electronic configuration of calcium and 4s. Okay, after 4s it is 3d. After 4s it is 3d. Actually 3d according to increasing order of energy. Here 3d is above 4s but below 4p. Okay, that's why in electronic configuration of scandium, see here 1s2, scandium it is 21. Okay, so 1s2, 2s2, 2p6, 3s2, 3p6. Okay, this is 18. This is 18. So you can mark it like argon in a square bracket. Okay, so 1s2, 2s2, 2p6, 3s2, 3p6. After that 4s2. Okay, 20 electrons will come like this: 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. So after 3p6, 4s2. After 3p6, 4s2, 4s2. After 4s2, 3d1. Okay, so this is the way of writing. We will write first 3d1, then 4s2. 3d1, 4s2. But electrons are filling 4s first. Okay, we have to write according to this order: 1s2, 2s2, 2p6, 3s2, 3p6. After 3p6, we have to fill electrons in 4s. We know after 3p it is 4s. After 3p we will fill electrons in 4s. After 4s we will fill electrons in 3d1. Okay. So next element after scandium, titanium. Titanium it is 22. So we will do accordingly 4s2, 3d2. We can fill electrons according to same order. We will fill accordingly. We have to fill electron after 3p6, 4s2. After 4s2, 3d2. For titanium, atomic number 22. So after 4s2, 3d2. Clear? So here we discussed This is electronic configuration of calcium. Calcium, it is 3p6 4s2. 3p6 4s2. After calcium, a new orbital 3d occupied here. Okay, so here actually according to energy order, after 4s 3d, then 4p. Here 3d is between 4s and 4p. Clear? And here for scandium 1s2, this is the order of writing. Okay, here 3p. After 3p6 4s2, we have to fill electron 4s2, then 3d1. For titanium 3p6 4s2, then 3d2. We have to fill electron accordingly. Okay, here 4p, you can remove 4p. Here 4p is 4p, there is no electron, so you can remove it. Okay, and we have to follow this pattern till zinc, scandium, titanium, vanadium, chromium, manganese. Okay, we have to follow this method until scandium. Clear? Okay, next one, we have to discuss here electronic configuration of chromium and copper. We discussed electronic configuration of different type of elements. Here we have two exception case, electronic configuration of chromium and electronic configuration of copper. Okay, chromium atomic number 24. Okay, so see here, chromium atomic number 24. This is the electronic configuration: 1s2, 2s2, 2p6, 3s2, 3p6, 3d4, 4s2. 1s, 2s, 2p, 3s, 3p, 3d, 4s. Okay, when you write this subshell electronic configuration and fill electrons accordingly. Okay, so here 24 electron. So the electronic configuration coming like this. This is the outer shell electronic configuration 3d4 4s2. 3d4 4s2. So actually this 3d4 4s2, it is wrong. There is one exception case in chromium and copper. Okay, here instead of 3d4 4s2, we have to write 3d5 4s1. Here one of this electron will move to this 3d and it will stay like this, 3d5 4s1. This is the subshell electronic configuration of chromium. Okay, here this is 18 electron. Okay, this part it is 18 electron and it is noble gas configuration argon. So after argon we have to write here 3d5 4s1. 3d5 4s1. One electron will move from s orbital to d orbital. I will tell you what is the reason. Okay, after that see here copper here 29 electron. Copper 29 electron. So electronic configuration coming like this. Okay, here 3d9 4s2. 3d9 4s2, actually it is wrong. Here one of this electron 4s electron move to 3d, then we have to write it like this, 3d10 4s1. Here it is 3d5 4s1. Here it is 3d10 4s1. Okay, 3d10 4s1. Clear? Here this part 18 electrons, so we can write it argon, then 3d10 4s1. Here reason for this, we know sp,d, f. S subshell we can accommodate 2 electron, p orbital, s orbital or s subshell 2, here 6, here 10, here 14. These are the maximum electrons we can accommodate these subshells. Okay, it's half. Here 2, it's half 1, 6, half 3, 10, half 5, 14, it's half 7. Here you have to understand half filled configuration. This is called half filled. These orbitals are half filled. Okay, and here these are completely filled. These are completely filled. Half filled and completely filled orbitals are highly stable. Okay, so here look here. here 3d4 4s2. This is the outer shell electronic configuration 3d4 4s2. So this is outer shell 3d4. Okay, it is not half filled or completely filled. That's why it is not stable. That's why one of the electron from 4s will jump to 3d, then it will change to 3d5 4s1. 3d5 4s1, 3d5 4s1. Now it is half filled, d5 half filled. That's why it is more stable. That's why it is stable configuration of chromium. Similarly here 3d9, outer shell 3d9, not half filled or full filled. That's why one of the electron will move from 4s to 3d, then it became 3d10. 3d10 means it is full filled. Full filled and half filled configurations are highly stable than compared to others. That's why here this configuration for chromium and copper, not this and this. So remember these two exception case for chromium and copper electronic configuration coming like this. Clear. Next one we have to discuss here orbitals and periodic table. Relation between subshell electronic configuration and periodic table. We know periodic table, this figure represent periodic table, and here periodic table we can see period and group. There are 18 groups in periodic table. Group 1, group 2, group 3, 4, here till group 12, then group 13, 14 till group 18. Okay, so here in periodic table elements which coming first two group 1 and group 2, this is called S block element. Elements which coming group 13 to group 18, these elements are called P block elements. And elements which coming this part, it is called D block element. From 3 to 12, group 3 to 12, it is called D block elements. Reason for this, the subshell electronic configuration of these elements end in S orbital. That's why these elements are called S block elements. Subshell electronic configuration of these elements end in P block, P subshell. That's why these elements are called P block element. Okay, similarly here subshell electronic configuration of this element end in D subshell. That's why it is called the D block elements. See here example, lithium. Here you can see lithium in first group. Okay, so lithium atomic number 3, 1s2, 2s1, 2s1. Subshell electronic configuration S orbital. Okay, 2s1. Look here all this element, it will be 2s1. It will be all this element will be s1, S subshell. Okay, and here one electron. That's why it's first group. And here you can see the elements which coming group 2, it will be s2, S subshell. There will be 2 electron. It is group 2. Okay, so generally you understand the elements which coming this part, their electronic configuration end in subshell S. Similarly here, look here, one example here, boron here, boron atomic number 5, 1s2, 2s2, 2p1. So subshell electronic configuration coming 2p, p orbital or p subshell. So these elements are called P block elements. You can check all these elements subshell electronic configuration end in p orbital or p subshell. Okay, next here D block elements. You can see here first element scandium atomic number 21. So their electronic configuration after argon 3d1 4s2. So this is the outer shell, not this one 3d. We know 4s 3d after 4s. Okay, we discussed before 4s 3d 4p. This is the order of energy, 4s 3d 4p. So here 3d1. So all these elements outer shell electronic configuration end in D subshell. that's why all these elements are included, or all these elements together called D block elements. S block elements, P block elements, D block elements. Clear? Okay, so here we discussed electronic configuration. We discussed subshell electronic configuration. We can use boxes to represent orbitals for electronic configuration. Look here, we can use this type of boxes for subshell electronic configuration. Here each box represents atomic orbital. We can use this type of box for electronic configuration. Each box represent atomic orbital. Each box can accommodate maximum 2 electron. Each box can accommodate maximum 2 electron. These electrons can be represent using arrow mark. Okay, see here, each box can accommodate maximum 2 electron. Okay, this box there is 2 arrow mark. This 2 arrow mark showing here this box or this atomic orbital which contain 2 electron. Okay, each arrow mark represent electron. See here, one box with 2 electron. Here each arrow mark, the direction of each arrow mark will be different. Okay, opposite direction. Clear? So here one box with 2 arrow mark showing 2 electron. Okay, here one atomic orbital can accommodate maximum 2 electron. This electron will spin its own axis. Okay, the spin of electrons will be opposite direction. Imagine one atomic orbital which contains 2 electron. Each electron spin opposite direction, one clockwise direction and another one anti-clockwise direction. Here this is atomic orbital, here 2 electron. Okay, here the spin direction is opposite. Here the direction of arrow mark different, it's showing the direction of spin of electrons are different direction. Clear? Next point we have to understand here, electrons in same region or same space, they repel each other because electrons have negative charge. Okay, many electrons in same region, they will repel each other because electrons have negative charge. Negative charge, two negatively charged species repel each other. Okay, look here, this is 2p orbital. We know p orbital, which p subshell, which contain 3 orbital, px, py, pz. Okay, here we have to know each orbital. Here orbital cannot pair. Here this orbital cannot pair until each orbital accommodate 1 electron. Clear? Imagine here P4, okay, or something P4. Okay, so you cannot do like this. You cannot pair this orbital before all orbital completely filled. Okay, first we have to fill all orbital completely, then only we have to pair. Okay, also during pair we have to fill electrons with the opposite spin. Imagine one orbital which contains 2 electrons like this. Okay, so the direction of arrow mark should be different. It indicates that 2 electrons in one orbital, their direction of spin is different. One is clockwise direction and another one anti-clockwise direction. Clear? So these are the things we have to remember here. We already discussed subshell electronic configuration. Boxes can be used for subshell electronic configuration. Each box represents atomic orbital. Okay, boxes are arranged according to their energy. We know atomic orbitals are arranging according to their energy. Similarly here, if you are using boxes instead of atomic orbital, we have to arrange them according to their energy. Okay. And another one here, electrons in the box represented by arrow mark. This type of arrow mark using to represent electrons in boxes. The direction of arrows represent spin of electron. We discuss imagine one orbital contain two electron, both electron will spin. One electron spin clockwise direction and another electron spin anti-clockwise direction. So spin of electron, the direction of spin of electron will be different. Clear? Here another thing we have to understand, electron will stay separate box until all box completely paired. That's we discussed. We cannot pair the boxes until each box completely filled. Okay, imagine here 4 electrons, so we have to make all unpaired. We have to make all boxes with 1 electron, then only you have to make it pair. Clear? And during the pairing of electron pairing we can do with the opposite direction to show the direction of spin of electron are different. Here another point we have to remember here, electrons in the same region or same space, they repel each other because electrons have negatively charged. Okay, so here boxes can be used to represent electrons of electronic configuration, and each box we can put electrons. Okay, and I will give you more example for this. Okay, here we have some example for subshell electronic configuration with boxes. Okay, so here I used here boxes to represent subshell electronic configuration. Here this first one, it represent 1s, the second one 2s, third one 2p, 1s, 2s, 2p. Okay, so we know subshell electronic configuration 1s, 2s, 2p, 3s, 3p. So we will use boxes accordingly, 1s, 2s, 2p, etc. Okay, we know S orbital. Look here, S orbital, SPD. Okay, S orbital, SPD. We know S orbital, there is S subshell, there is 1 orbital. P subshell, there is 3 orbital. D subshell, there is 5 orbital. S subshell 1 orbital, P 3 orbital, D 5 orbital. So similarly, look here, S subshell here 1 box mean 1 orbital. Here P mean 3 orbital. P, there will be 3 orbital, Px, Py, Pz. Okay, so here imagine 2p3. 2p3 mean here 3 electron. In 2p subshell there is 3 electron. Okay, so here first electron will go to px, second one py, third one pz. Okay, so this is 2px, 2py, 2pz. Here all these orbitals, they have same energy. Also this electron, the direction of electrons are same. Okay, so they have same spin, also they have same energy. Okay, here look, here it is 1s, 2s, 2p. So 1s less energy than 2s, less energy than 2p. So this is the graphical representation for different orbitals according to their energy. Here you can see px, py, pz, they have same energy. Okay, so here we have 2p3. 2p3 mean p orbital with 3 electron. So these 3 electrons we cannot fill like this. 3 electrons we cannot fill like this. It is wrong method. It is wrong. Okay, we have to fill this completely. We have to fill this completely. Okay, these are called half filled configuration. We have to complete all half filled. Okay, then we have to fill. Then we have to pair it. Okay, first fill completely, then only you can pair it. Look here, 2p4. 2p4 you cannot do like this. 2p4, it is wrong. We cannot do like this. Okay, first we have to fill it completely. 1, 2, 3. All this same spin, same energy. Then you have to pair it. First fill it completely. Okay, then we have to make it pair. During pairing, we have to make sure that the arrows are different direction, opposite direction. This opposite direction means the spin of electrons are in opposite direction. Okay, here all are in same direction, but during pairing we have to make it opposite direction. Clear? Now see here S1 orbital, P 3 orbitals, D we know 5 orbitals. Okay, D there will be 5 orbital. 1, 2, 3, 4, 5. Different 5D orbitals you will study later. Shape of 5D orbitals you will study A2. Okay, now see here. Let us check subshell electronic configuration of carbon. Carbon we know 1s2, 2s2, 2p2. 6 electron carbon. 2, 4, 6. So we can do it like this. Here 2 electron. 1s2 mean here 2 electron with the opposite spin. 2s2 also 2 electron with the opposite spin. Here 2p2 we have to do like this. Do not make it pair. We have to fill each box 1 electron. Okay, after completely fill, then you can make it pair. Clear? Look here, oxygen atomic number 8. So here it will be 1s2, 2s2, then it will be 2p4, 2, 2, 4. That is oxygen 8. Okay, so here 2 electron, here also 2 electron, here 4 electron. 1, 2, 3, same spin. Then make it pair with opposite spin. Clear? Nitrogen atomic number 7. 1s2, 2s2, 2p3. 1s2, 2s2, 2p3. Here 2 electron with opposite spin. 2 electron with opposite spin. Here 3 electron. So here 3 electron in 3 different orbital. 3 electron in 3 different box. Okay, and all are in same direction, same energy. Okay, so here 2p3. You can say 2p3 contain 3 electron with the same spin and same energy. Clear? So these are the things you have to understand here. Subshell electronic configuration using boxes. Clear? Okay, next one we have to discuss here subshell electronic configuration of ions. We discussed subshell electronic configuration of atom. For example, we know subshell electronic configuration of sodium. Sodium atomic number 11. So it will be 1s2, 2s2, 2p6, 3s1, 2, 4, 10, 11. This is normal electronic configuration of sodium. Okay, we know there are 2 type of ions. There are 2 different type of ions. Positively charged ion, negatively charged ion. Positively charged ions. Example for positively charged ion: Na plus, titanium 2 plus, chromium 2 plus. These are different type of positively charged ion. Positively charged ion mean atoms, positively charged ions mean these atoms have less number of electron. Atoms after losing electron they will change to positively charged atom. Okay, Na plus mean 1 electron less. Here titanium 2 plus mean 2 electron less. Al 3 plus mean 3 electron less. Okay, so look here, subshell electronic configuration of sodium this. So Na plus mean there will be 1 electron less, 1 electron less. So here it will be 3s1, it will be 0. So you can do it like this, 1s2, 2s2, 2p6, 2p6, 3s0, or you can write like this. Because Na plus mean not 11 electron, there is 10 electron only, 10 electron. So 2, 4, 10. This is subshell electronic configuration of Na plus. Okay, look here, titanium atomic number 22. So argon mean now it is 18. Then 3d 4s. We have to fill electron first 4s, then 3d. Here 18, 20, 22. This is subshell electronic configuration of titanium. Titanium 2 plus mean 2 electron less. 2 electron less mean here argon 3d2 4s 0. Okay, so here we have to fill electron first 4s, also we have to remove electron first from 4s. Here actually 3d2 4s2. Okay, titanium 2 plus mean 2 electron less, so we have to remove these 2 electron. Clear? Here actually during filling electron first we will fill electron 4s2, then only we will fill 3d2. When you are removing electron, also you have to remove electron first from 4s. After completely removing from 4s, then only you can remove electron from 3d. Clear? So this is titanium 2 plus. Titanium 2 plus. Okay. So similarly you can do chromium. Chromium atomic number 24. So chromium 2 plus mean it will be 22. So you can do this subshell electronic configuration and you can do it in comment box. Okay. Now see here, this is subshell electronic configuration of positively charged ion mean there is electrons are less. Now see here negatively charged ion. Negatively charged ions mean number of electrons are more number of electrons. For example here chlorine. For example here negatively charged ion Cl minus, O2 minus, N3 minus, etc. Chlorine atomic number 17. Cl minus mean minus 1. Minus 1 mean 1 electron more. So chlorine. Cl minus mean there will be 18 electron. O2 minus, actually oxygen atomic number 8. O2 minus mean 2 electron more. So here 10 electron. Similarly here nitrogen atomic number 7. 3 minus mean 3 electron more. N3 minus mean there will be 10 electron. Okay. So here chlorine. Here 1s2, 2s2, 2p6, 3s2, 3p5. Okay. 2, 4, 10, 12, 17. This is the subshell electronic configuration of chlorine. Cl minus mean 1 more electron. So you have to repeat all this. At the end there will be 1 more electron. 3p6. Okay, 3p6. Actually 3p5 we have to add 1 more electron because Cl minus. Here see last example sulfur. Sulfur atomic number 16. Okay, so 1s, 2s, 2p, 3s, 3p. 3p. So here 2, 4, 10, 12, 12, then 4. This is 16. Okay. 2, 4, 10, 12, then 12 plus 4 16. This is subshell electronic configuration of sulfur. Okay, S2 minus mean 2 electron more. Sulfur atomic number 16. S2 minus mean 2 electron more. So there will be 18 electron. So you have to repeat all this. At the end 3p4 will change to 3p6 because there will be 2 more electron, 2 extra electron. So here all this repeat at the end. Instead of 3p4 it will be 3p6. Clear? So this is subshell electronic configuration of ions. So positively charged ions mean you have to remove electron. Okay, you have to decrease number of electron. Negatively charged ions mean you have to increase number of ions. Okay. Also from scandium to titanium you have to remove electron from 4s. You have to remove electron from 4s. After completely removed, then you have to remove from 3D. Clear? Okay, next one we have to discuss here patterns of ionization energy in periodic table. Okay, here we have to discuss here in periodic table. We know there is group and period. In period, one example for period: lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. This is one period. Okay, when you are moving from left to right in period, ionization energy generally increases. Ionization energy of different first ionization energy of elements increases from left to right in period because when you moving from left to right, effective nuclear charge increases, number of protons increases, effective nuclear charge increases. That's why ionization energy increases. Also there is one more reason here. When you are moving from left to right, look here lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. Atomic number 3, 4, 5, 6, 7, 8, 9, 10. Okay, this is atomic number. So here electronic configuration 2, 1, 2, 2, 2, 3, etc. It's coming like this. So you can observe here 2 orbit, here 2, here 2. All case there is 2 orbit. Number of orbit not increase. Okay, all case there is 2 orbit only. So number of orbit not increasing. Number of orbit not increasing. So you can say shielding remain constant. Here shielding, shielding mean inertial electron make a barrier between attraction of nucleus and outer shell electron. Inertial electrons make a barrier between nucleus and outer shell electron. This barrier, that is shielding. Okay, so if there are more number of inertial electron, more shielding. Okay, but in this case number of inertials are constant, remain constant. So you can say here shielding remain constant, but number of protons increases from left to right. Shielding remain constant, but number of protons increases from left to right. Okay, number of protons increases, effective nuclear charge increases. So nucleus attract outer shell electron more effectively. That's why ionization energy generally increases. We have to give more energy to remove outer shell electron. Okay, attraction between nucleus and the outer shell electron increases because of effective nuclear charge, and we have to give more energy to remove outer shell electron. Clear? So these are the 2 reasons to increase ionization energy across the period. Okay, first one, effective nuclear number of protons increases, effective nuclear charge increases, but shielding remain constant. Okay, so here we discuss these things. Okay, so here you can see when you observe first period, second period, okay, the last element of one of the period and the first element of next period. Here ionization energy of last element in a period and ionization energy of next element in next period, there will be big difference. Okay, so you can say here ionization energy of this E2 is much less than E1. Example here, when you consider helium and lithium, ionization energy of helium is much higher than lithium. So here I said ionization energy of last element in a period is much higher than ionization energy of next element in next period. Okay, so this reason we are talking why this ionization energy difference like this. Example here, when you consider helium and lithium, helium is one of the element in one period and lithium is next element in next period. So you can see much big difference there. Okay. So reason for this, when you consider helium and lithium, helium atomic number 2, subshell electronic configuration 1s2. Lithium atomic number 3, subshell electronic configuration 2s2 and 1s2 and 2s1. 1s2 and 2s1. So you can observe here in lithium there are 2 orbits. There is one additional orbit. Okay, so distance between nucleus and outer shell electron will be increases. Okay, so less energy needed to break this, less energy needed to remove this electron. Clear? So one reason here, second element consists of one additional orbit. So distance between nucleus and outer shell electron will be increases and less energy needed to remove outer shell electron. Okay. Also second reason, see here when you consider this and this, here inner shell electron, there are inner shell electron. So here next reason, second element consists of inner shell electron. This inner shell electrons act as a barrier between nucleus and outer shell electron. Okay. Also you can say this inner shell electrons produce inter-electronic repulsion. Here this is first orbit, this is second orbit. Each orbit consists of electron. Electrons have negative charge and there is inter-electronic repulsion. Inter-electronic repulsion, electron-electron repulsion. That's why outer shell electron try to stay maximum apart and we can remove this electron very easily. So there are two reasons for second element showing less ionization energy. First reason, second element consists of one additional orbit. So distance between nucleus and outer shell electron increases and we can remove outer shell electron very easily from this element. Second element consists of inner shell electron. This inner shell electron produce shielding effect. Also there will be inter-electronic repulsion. Okay, so here generally you understand across the period ionization energy increases. Okay, reason effective nuclear charge increases but shielding effect remain constant. Okay, so here we discussed general trend in ionization energy. Across the period. Across the period, ionization energy generally increases. When you move from left to right in a period, ionization energy generally increases. You can say generally increases. You can see there are many exception case. See here one exception case. Here beryllium and boron. Beryllium atomic number 4 and beryllium atomic number 4, boron atomic number 5. We discussed across the period number of protons increases, effective nuclear charge increases. That's why ionization energy generally increases. But when you consider beryllium, number of proton less than number of protons inside boron. Okay, number of protons in beryllium less than boron. Okay, beryllium less than boron. But ionization energy of beryllium is higher, even its number of proton less, but ionization energy higher. Reason for this, we can explain its reason based on their subshell electronic configuration. Beryllium atomic number for its subshell electronic configuration 1s2 2s2. Similarly, boron its subshell electronic configuration 1s2 2s2 2p1. So when you consider boron and beryllium, in boron outer shell electron, this is outer shell electron, it is little bit far, slightly far. Okay, this outer shell electron slightly far from nucleus compared to beryllium. Outer shell electron of boron is slightly far. Okay, that's why distance between nucleus and outer shell electron is slightly higher. Okay, that's why ionization energy of boron is less than beryllium. Okay, one reason here, distance between outer shell electron and nucleus slightly higher. Okay, slightly higher, not a big difference, slightly higher. That's why ionization energy of beryllium is higher than boron. Also, second reason, in boron there are inner shell electron. This is outer shell. Okay, so there are inner shell electron. This inner shell electron in boron make a barrier, make a shielding between outer shell electron and nucleus. Okay, so there is shielding effect in boron. Okay, slightly shielding effect is slightly higher in boron compared to beryllium. Okay, shielding effect slightly higher. Also, you can say here inner shell electrons are there. This inner shell electrons make a inter-electronic repulsion. Inter-electronic repulsion. Here each orbitals there is electrons have negative charge. Okay, so there will be inter-electronic repulsion. This inter-electron, because of this inter-electronic repulsion, outer shell electron try to stay maximum apart, slightly, not a big difference, slightly stay apart from nucleus. Okay, that's why we can remove this outer shell electron easily compared to beryllium. So these are the two reasons here. Distance between nucleus and outer shell electron slightly higher. Second one here, shielding effect is slightly higher. These are the two reasons here. Beryllium has higher ionization energy compared to boron. Clear? Here another exception case, nitrogen and oxygen, same reason, same observation we can see here. Nitrogen and oxygen, nitrogen atomic number 7, oxygen atomic number 8. Here less number of proton, okay, even its ionization energy higher than oxygen. This reason we can explain this, not same reason, here different reason. Okay, here also we can explain this reason based on their subshell electronic configuration. Nitrogen 7 1s2 2s2 2p3. Okay, oxygen 8 1s2 2s2 2p4. This is subshell electronic configuration. So see here 2p3, here 2p4. I took this 2p3 and 2p4 here. Okay, 2p3 we learned before, we have to fill electrons completely, then only we have to pair. Okay, so here pairing not occurs. In 2p3 not pairing occurred. There is no pairing. But in 2p4 there is pairing. There is pairing occurs. Okay, so here we have to understand. here 2p4. So in oxygen, outer shell electron is removed from an orbital which contain paired electron. 2p4, there is paired electron. So in oxygen, outer shell electron is removed from a paired electron, a paired orbital. Paired orbital mean here paired electron produce an extra electronic repulsion. Compared to this one, here there are paired electron. This paired electron produce an extra repulsion, because all these electrons negative charge, so there will be an extra repulsion in paired electron. Okay, so because of this repulsion, it is called spin pair repulsion. So you can remember this name, spin pair repulsion. So here in oxygen there is spin pair repulsion. Okay, in oxygen there is spin pair repulsion. Nitrogen there is no spin pair repulsion. That's why nitrogen has slightly higher ionization energy than oxygen. Even oxygen contains more number of protons than nitrogen. So here reason distance between nucleus and the outer shell electron slightly higher. Also there is shielding effect in boron. Okay, that's why less ionization energy. But here when you consider nitrogen and oxygen, you can write down the subshell electronic configuration. Nitrogen outer shell electronic configuration 2p3. But here oxygen outer shell electronic configuration, it is 2p4. 2p4 means there is pairing occurs. Okay, pairing occurs. Here in oxygen, outer shell electron is removed from an orbital which contain paired electron, and this, because of this pairing, it produces an extra electronic repulsion. We know if there is extra electronic repulsion, outer shell electron try to stay maximum distance. Okay, it try to stay little far because of the repulsion. Okay, so we can remove outer shell electron easily in oxygen. So ionization energy of oxygen is less than nitrogen. Clear? Next one, down the group. Here we have to discuss last point in this chapter, patterns of ionization energy or variation of ionization energy down the group. Variation of ionization energy down the group. For example, lithium, sodium, potassium, rubidium, cesium, francium. This is group 1. When you are moving from top to down, we know generally size of the atom increases, atomic number decreases, size of atom increases. Okay, so down the group, size of the atom increases. So we can say here, down the group, atomic radius increases. Atomic radius increases, distance between nucleus and outer shell electron increases. Okay, so less attraction between nucleus and outer shell electron. So we can remove outer shell electron very easily. So ionization energy decreases. Generally down the group, ionization energy decreases. Reason, size of the atom increases or atomic radius increases, attraction between nucleus and outer shell electron increases. That's why it needs less energy to remove outer shell electron. Clear? Also here, when you are moving from top to down, inner shell electrons increases. Okay, inner shell electrons increases, number of inner shell electron increases, and this inner shell electrons make a barrier between nucleus and outer shell electron. So you can say shielding effect increases. Okay, a shielding effect between nucleus and outer shell electron increases. Okay, so these are the two reasons to decrease ionization energy down the group. First one, atomic radius increases or size of the atom increases, less attraction between nucleus and outer shell electron. Second reason, number of inner shell electrons increases. Both the number of inner shell and inner shell electrons increases. these inertial electrons make a shielding between nucleus and outer shell electron. So shielding effect increases down the group. Okay, so these are the things we have to understand in this chapter. You can review the video once again. Okay, if you have any query, you can put your doubts in comment box. Okay, so thank you for watching this channel.